Imagine trying to build a mathematical space entirely out of clusters. You want a structure where no single point sits alone, isolated from the rest. Every single coordinate must be surrounded by an infinite swarm of immediate neighbors, yet you don't want them to form a solid object. Now try the opposite problem. Take a perfectly solid, continuous line segment and try to snap it into two separate open pieces without leaving a gap or losing a point in the middle. Geometric intuition suggests you can just cut it in half. Mathematical rigor proves you can't. The text that definitively resolves both of these problems is Walter Rudin's Principles of Mathematical Analysis. Specifically, the answers lie in Chapter 2, where Rudin lays out the topological rules that govern the structure of the real number line. We are going to look closely at the section defining perfect sets. The structure of the real line relies on a precise dichotomy. Perfect sets dictate the rules of infinite density and cardinality. Connected sets dictate the rules of continuous geometry. Connectedness is the strict logical engine that makes continuous lines possible, while perfect sets expose a deeply counterintuitive relationship between infinite clusters and uncountable size. Mastering the distinction between these two topologies is the mandatory gateway for anyone looking to survive a graduate-level real analysis exam. A perfect set meets two conditions. It is closed, containing all limit points, and has no isolated points. For example, a solid interval AB. It includes its boundaries, and any microscopic point inside is surrounded by infinitely many neighbors. An open interval fails this test because it doesn't contain its outer boundaries. The set of all integers fails because every number is separated by a gap of 1. They are entirely isolated. Theorem 2.43 states that any non-empty perfect set must be uncountable. Rudin proves this by contradiction. He assumes the perfect set P is countable, theoretically arranging its elements into a numbered list, x1, x2, x3, and so on. Assuming the list exists, we draw a boundary, v1, around the first point, x1. Since x1 isn't isolated, we pick a neighbor, x2, and draw a smaller boundary, v2, explicitly excluding x1. Repeating to infinity, we create shrinking nested boundaries. A known property of these compact nested sets is that their infinite intersection cannot be empty. There must be at least one mathematical coordinate trapped at the absolute center of these shrinking rings. But the center point cannot be x1, because we excluded it in step 2. It cannot be x2, because we excluded it in step 3. In fact, we deliberately excluded every single point on our supposedly complete countable list. The center point was successfully hidden from the list. Any set built entirely out of its own limit points holds so much dense recursive structure that it is strictly impossible to count its elements. Theorem 2.43 leads directly to a notorious topological structure, the Cantor set. We construct it starting with a closed interval from 0 to 1. We iteratively delete the open middle third of every remaining line segment out to infinity. The Cantor set is whatever topological material survives this infinite sequence of deletions. Visually, it looks like a scattered field of disconnected dust, yet it strictly qualifies as a perfect set. Whenever we remove a middle section, the boundary endpoints of the remaining pieces are never deleted. Because we do this infinitely, every surviving point is flanked by other surviving points at arbitrarily small distances. There are no isolated dots. Since all perfect sets are uncountable, this scattered dust contains the exact same uncountable infinity of points as the solid line we started with. This text shows the mathematical proof proving the second half of the Cantor paradox. Equation 24 demonstrates that the set contains 0 continuous segments. If you propose that a segment of any specific length managed to survive the deletions, the math allows us to simply run the fractional removal process a few more times. We can easily force the remaining Cantor fragments to be strictly smaller than your proposed segment. No solid line, no matter how microscopic, can fit inside the Cantor set. Its total geometric length is exactly 0. Uncountable size doesn't require area. The Cantor set forces a total separation between our geometric intuition of physical length and the topological reality of infinity. If perfect sets explain the counterintuitive density of dust, we need a different topological rule to explain solid, unbroken continuums. Rudin defines this through the concept of separated sets, shown here in definition 2.45. Sets A and B are separated if and only if neither set contains a limit point of the other. The points of A must be kept completely clear of the closure of B. Disjoint sets are not automatically separated. Just because two sets don't share identical elements does not mean they are topologically detached. Take the open interval from 0 to 1 and the closed interval from 1 to 2. They don't overlap, they share 0 numbers. But the closure of the first set includes the number 1. That limit point acts as a topological glue, binding the two sets together. They are disjoint, but they are not separated. We define a connected set negatively. A set is connected if it's strictly impossible to express it as the union of two separated pieces. Theorem 2.47 maps this precise definition directly to the real number line, proving the structural integrity of intervals. Suppose you have a connected set, E, with points x and y. Pick a point z located between them. If z is missing, the structure fails. The interval snaps into two separated halves, neither containing the limit point of the other. This text highlights the formula z equals the supremum of A intersected with x to y. By identifying the exact upper boundary of the lower half, the math exposes the gap. If the set can snap at z, it is separated, and therefore not connected. To maintain a single continuum, every intermediate point must exist. Connectedness is the strict topological machinery proving what our eyes perceive as an unbroken line. The architecture of the real line relies heavily on these two structural definitions. Perfect sets are closed boundaries comprised entirely of limit points. They prove that you can possess uncountable infinity even when your total geometric length is reduced to 0. Connected sets are structures completely incapable of being divided into separated pieces. They provide the logical proof that lines and intervals are continuous. These specific theorems are heavily tested in graduate entrance exams, like the IIT JAM or TIFR, because they check whether a student has successfully replaced their physical intuition with formal logic. Grasping the Cantor set's zero-measure paradox is a non-negotiable prerequisite. You cannot successfully study Lebesgue integration later in the text without it. Likewise, understanding connectedness is the required foundation for proving the intermediate value theorem and properly mapping continuous functions across real space. Geometry gives us a visual representation of the math, but topology is the true operating system compiling the code beneath it. If you want to continue deconstructing the logic behind classic mathematical texts like Rudin's PMA, subscribe to the channel for